Okay, this is Paul Liu from North Carolina State University. Welcome again to this World River and Delta System Source to Sink webinar series. And today we invite Sepehr Eslami from Utrecht University come here to talk about salt water intrusion in the Mekong Delta. So before I introduce Sepehr, so in this next week, Wednesday, we will have one Sepehr come here talk about Magdalena River, and so the sediment load and with the impact of and the human being impact, and also that sediment load change, the trend and the impacts on coastal ecosystem. And followed by that, we will have Paul Schuster come here talk about the Yukon River, and then next talk about the Mississippi River. Okay, once again, this talk series, now we have more than 70 talks archived on our YouTube channel. So if you go to the YouTube Source to Sink, or you can go to tinyurl.com/S2S talks, a short link, then you can directly come in here. All the talk have already been archived there. And or you can subscribe to this channel, automatically remind you when the new presentation being uploaded. And at the same time, you're also welcome to follow our Twitter account, Source to Sink. So over there, we will post weekly the new talk, the notice. Okay, Sepehr Eslami is a coastal engineer, and also he studied the Delta system. Currently, he's a PhD fellow, will defense and get a degree very soon. And his dissertation is environmental change in a mega delta, particularly focused on the Vietnam Mekong Delta. And currently, he is the senior research and advisor at the Singapore branch office of Deltavis. So focused on the marine and the coastal dynamic, in that unit, and try to understand climate adaptation strategy on deltas. So Sepehr, now you can share your screen and put a presentation mode.
You see my my screen?
Yes.
All right, great. Thanks a lot, Paul, for the introduction and in general for the platform. Great initiative. We are all big fans. So this work I'm presenting here on salt intrusion in Mekong Delta, it's been a roller coaster of cooperations with different people and different institutes that have contributed. I've listed them here, but I'm sure they accept my apology for not mentioning all the names. Hopefully it stays in the archives for all that helped us in this project over the last 6 years, 5-6 years. The main part of this project is part of the Rise and Fall project at Utrecht University, but it has been, of course, co-funded by other institutes and a lot of cooperations between different universities and institutes. In this talk, I discuss a little bit about the Mekong River Basin, discuss a little bit about salinity and tides in the Mekong Delta, and touch upon the extreme salinity events and present salinity dynamics. This is the let's say the first half of the presentation, which might get a little bit into details of processes. So that's for those who are interested mainly in estuarine dynamics. Might get a bit too technical, and then we look into historical trends and the projections of saltwater intrusion as an integrated system approach, which is, in my opinion, a little bit more for a broader audience that can easily relate to that type of content. So if you look at the Mekong River Basin, it runs through 5 countries and transports 300 to 500 billion cubic meter of fresh water per year. Something in the order of 20 to 160 million ton of sediment per year. The upper limit of that number comes from the historical values. Right now, we are much closer to the lower bound. The system is extremely seasonal in response to the Southeast Asian monsoon. So for instance, in this figure, as we see, if you see my mouse, it's located, this is where the Mekong Delta is. And in the Northern Hemisphere winter time, we basically have northeastern monsoon. And then you see the predominantly northeasterly wind blowing over the South China Sea and Vietnam. And then in the Northern Hemisphere winter, you see that this reverses and it turns to southwestern monsoon. If we look at what it means in terms of water balance, the northeastern monsoon coincides with the dry season of the Mekong. So if we look at this black line, which is the daily discharge at a station called Kratie in Cambodia. It's very low, down to, let's say, 3,000-4,000 cubic meter per second. And if we go during the southwestern monsoon, this turns to that then comes with the wet season, which we can reach values of 40,000 cubic meter per second in the river. So the system is extremely seasonal, but it's also subject to significant anthropogenic influence. This is the number of currently existing operational hydropower dams. A number of them have been operational over just the last 5-6 years, and there are plenty of more hydropower and irrigation and conversion dams on the tributaries. The system is also subject to significant sand mining. We have most of this sand mining along the Mekong River is apparently happening in Cambodia, but also in Laos and Vietnam. We also see significant amounts of sand mining. Down to the delta, the Mekong Delta itself, I very much like this aerial picture of the delta. It's often referred to as the rice bowl of Southeast Asia. It's a heavily the land use within the Mekong Delta is heavily related to agriculture and aquaculture. It extracts something in the order of 80 million cubic meter per day of surface water from them, and in the order of 2 to 2.5 million cubic groundwater from the characterizes the delta, and it provides 50% of the nation's food and 22 million and hosts 22 million of population. So on that note, if we just have some impression of the delta for those who haven't been, so these are some pictures of rice plantations in the northern delta and some canals, primary and secondary canals that are used for navigation and irrigation. This is another picture that shows anthropogenic impact. At times, these images can be seen. We see a significant number of sand barges in the delta that basically is one of the major drivers of change in the delta over the past 2 decades. We have a nice aerial picture of one of the branches, the Hao River, one of the branches of the Mekong River in the delta, and you see the huge dimensions of the river system. This is one sand barge, and here we're talking about 2 to 4 kilometer width of the channels. Back to seasonality and on hydrodynamics of the delta. If we look at the delta itself, this is a vulnerability map that's developed by my colleague Philip Mendehout. as you see, the lower the delta, the closer we get to the sea level, the lower these numbers, the more red the colors get. So the delta is extremely low lying. And in fact, the average elevation of the delta is estimated around 80 centimeters from the mean sea level. The Mekong River, once it enters the delta, actually already in Cambodia, it splits into two branches, the Tien system and the Basak system, or Hao system. These two branches, they further split into estuary and distributary channels. And if we look at some of the main stations in the Mekong Delta, we can see that during the dry season, which is the Northern Hemisphere winter season from January, February, March, April, we see that which coincides with the dry season. Therefore, we have higher tidal difference, and tidal difference can reach for instance, in this station Kanto, can reach up to 2 meters. And that tidal difference goes down to, let's say, 1.23 meter in the wet season. And then when we go further upstream, for instance, in this station, Chao Do, close to the Cambodian border, in the dry season, we have tidal difference of in the order of 1.3 meters, and that can reach nearly zero in the wet season. So the seasonality in discharge also translates into tidal dynamics of the delta. If we look at let's say static image of how tides propagate in the delta. This is an image from the dry season. You can see that tidal amplitudes gradually decrease when you travel upstream, and these lines, each of them basically the co-phase lines show the phase in minutes. So for instance, if the tidal wave is at this located estuary mouth at 125 minutes, it takes about 375 minutes to reach the Cambodian border. So this is more or less telling you how the tide travels along the estuarian channel. If you look at the freshwater discharge distribution, this is more or less an approximate discharge division between the channels. At the border, we have 85% division, but then a lot of that water is diverted to this channel again. So once we arrive close to the estuarian system, then we more or less come to equal cumulative discharge division. But this cumulative discharge division does not mean that there are no temporal changes. The system is extremely dynamic. So in this image, I have average discharge, the black line at this Kanto station. And we see that it's in the dry season from February to April. You see that it's jumping between, let's say, 2.5 to down to 500 cubic meter per second. And that's an average discharge. Of course, the tidal signal reaches up to 20,000 cubic meter per second. And if we plot that against average water level change, then we also see that this is also the subtidal or average water level is also changing significantly. And this is not the tidal signal. This is the non-tidal signal. And what we see, if we look closely, we can see some sort of a relationship there, or at least we can see that, for instance, these high water levels in peak sort of follows a high discharge. Here, for instance, it's also exaggerated, can be seen. We have another peak in water level that is followed sort of by a high water discharge. I will come back to this and explain what this actually resembles. We looked into this in more detail. If you look at just pure water level at subtidal water level, so average water level, at Kanto and then at Chao Dok. So the black line is most upstream at Cambodian border. They more or less follow the same let's say, average trend. And there is a strong correlation with wind speed. So if we look at the wind speed, this is a very clear one. If we see this huge wind, this peak in the monsoon wind, first you have to look at all of these wind speeds are basically westerly. So it's coming from east and going to the west during the north eastern monsoon. And you see that these peaks are normally followed by peaks in water level. So there's a clear correlation between wind over the South China Sea and East Sea and how it translates into surge and how that surge actually travels in the system. And there's also that sort of a reverse correlation between wind and discharge. So these are all, so for instance, here, if we look at this peak, it follows with a little bit of a delay by discharge, by a peak in discharge. So this is just to show and tease the topic that the system is it's changing very rapidly, very quickly to environmental changes. But it all for us started in 2016. When we started 2015, we started with this project. In 2016, there was this extreme drought event that was supposed to be the biggest salt intrusion in the history. And hearing that, although we didn't have any plans for field measurements, we felt obliged that this is the moment we actually have to document this event. At the same time, there were reports by UN on the drought situation. So the reports were coming in around January already, and then we were thinking of going to do these measurements in 2006. So it was quite an effort to arrange a field campaign within a very short period from the Netherlands, where we were back then, to mobilize and arrange a field campaign in Delta. So if we look, for instance, in fact, in 2015, there was a salt intrusion projection for the year 2050, and the 2016 drought actually exceeded that projection. Within 1 year, the projections for 2050 were actually exceeded in the Mekong Delta. So this was a historical event. But that was not the last time. In fact, in 2020, this again happened in an extreme level. And normally, salinity intrusion and drought is a natural process in the Delta. Every 7-8 years, you have drought events that are normally related to El Nino. But recently, these things are happening more often and more extreme, and the duration of salt intrusion period is longer. So that has become a significant concern. Back to our field campaign. So we went, we packed our bags and we went to the Delta. We went to this branch, and we basically decided to sail simultaneously with 2 boats, speedboats, at the estuary mouth, and travel upstream and measure salinity at intervals of 2 to 3 kilometers. Some impressions of our, well, of course, the objective was to measure the record salt intrusion. Some impressions of our field campaign: we had to set up a base camp in a parking lot of a motel in the middle of the Delta, with great support from our colleagues at the Southern Institute of Water Resources and Research in Ho Chi Minh City. This was one of our boats, and of course the beautiful mangroves and palm trees of the Delta. But talking about the measurements along these 2 channels, we measured salinity over depth, and what we saw was we measured nearly 50 kilometers during the neap tide. And then 1 week later, when we came back during the spring tide, we measured nearly 55 kilometers. And that was nowhere close to anything historical, because Guyana and Savannah in 2006 actually measured nearly the same numbers, while the reports coming out of the Delta were talking about 70-80 kilometers salt intrusion, and this was nowhere close to that historical value. So for us, it was a bit of a surprise and I have to say scientific disappointment, but we were happy for the delta that actually salt intrusion was not as much as we thought it would be. Nevertheless, the reports were still coming in, and in fact there were times that apparently salinity reached that level, but not during the period that we're measuring. And this was, of course, came with a lot of questions for us. Whether it's maybe fake news, but that was, of course, a joke. Despite the fact that we couldn't measure record salt intrusion, we did see extremely interesting patterns. So, for instance, in the neap tide along the two channels, Din An and Chande, the upper is the deeper channel and larger channel, the Din An channel, and we see that salinity structure, S2S salinity structure. So we see strong stratification in the neap tide, in the deeper and wider channel, while the shallower and narrower channel is a little bit more mixed. And when we come back in the spring tide, we do see that the salinity structure changes, and we have much more mixing in the system. The spring tide, of course, more energetic tidal system. But this, like I said, so we had this question: how did salinity change? Why did we not measure extreme salt intrusion? Of course, we were sort of aware of the temporal variations, but later on, when we could look back at the campaign and look at the measured signals, for instance, at this station, this was the variation of salinity. This is a depth average salinity at somewhere not too far from the riverbank. And these was the period of our field campaign, which you can see that it was during the dip in the salinity increase, in salinity values. And then when we start looking at this figure might start look ugly, but bear with me, it's going to be simplified. When we started looking at other drivers, we look at discharge, for instance, we see that, yes, indeed, there is this peak in discharge that I already showed, that, of course, it results in lower salt intrusion. Then we had this change in average water levels in Kanto, which was sort of related to wind, as I mentioned, ocean wind, as I mentioned. And then, of course, we had, if you look at this line, it's an indication of spring neap variability. So the higher the value, the higher this is basically spring tide. And we do see some sort of a increase in values during the spring tide, while it actually changed towards our field campaign. So in the springtide, towards end of springtide, we had higher values, but not necessarily during the springtide. And that was basically made this whole thing a little bit more complicated. And we had to resort to modeling. So we developed a very large 3D model of the Mekong Delta, basically all the way up to Cretier upstream, where we could assume daily variation, daily average discharge as a reasonable value, and downstream all the way to the 70-80 kilometers from the coast, where we could actually assume that salinity would remain constant and would not change too much. And then, of course, we added a lot of movable dams to the system, a lot of observation points, added the water demand, as I mentioned, is significant value, and tidal and subtidal signal. This is just an impression of the model, I have to admit, rigorous model calibration that we did. We see, for instance, here in these two are some two water level stations, and you see a relatively very good correlation between the model and the data, especially in the subtidal signal is very much regenerated by the model. Same goes for discharge. Here the same. This is water level discharge at Kanto, and then salinity at multiple stations. Of course, salinity, there is no way that we can have like water level a one-to-one comparison. It's a much more sophisticated measurement, as well as so the comparison it's not really a one-to-one, but it's more of a qualitative comparison, and we do see a very good trend and also a very good correlation in terms of salt intrusion length and the patterns, basically, as we observed. And what I haven't shown here is model performance on estuarian structure, which was also very much resembled the observations. So if I talking about this, and I promise these are my last 2-3 slides that are with these complicated figures, but if I look at the model results and showing the estuarian variability in time, if I look at flow profile, velocity profile over depth and in time, and these two dots are showing where we did our measurements. We do see that in the spring tide, so here is more of a spring tide, and then you see that there's a back and forth in the flow, and there's not much of a significant difference between velocities over depth. The black line shows the average salinity at this location, and this is estuarian salinity variation in time. And then when you see that in the spring tide, we do have a much more mixed system, and once we approach the neap tide, this variation we do get much more of a stratification in the system, and as well in the salt fluxes. So looking at all of these dynamics, we basically disintegrated the different components and in the model, and we just look, okay, if we just remove storm surge from the model, what happens to salinity? And so start here from the water level. So this is the blue line is the subtidal modeled subtidal water level, and once we remove the surge from the model, the red line, the red dashed line, gives you the subtidal water level in absence of surge, which basically is much more flat. If we look at discharge, we do see the black solid line is modeled with the surge, and once we remove the surge, you see that the peaks are starting to disappear in the model. And if you translate that to salinity, if this is the reference case with all the drivers, the moment we remove ocean surge from the model, we basically start underestimating and sometimes overestimating, but mainly underestimating salinity, especially at peak events. And that, again, is an indication that the system is extremely dynamic, and it rapidly responds to various environmental drivers such as discharge, storm surge, tidal variability, water demand, and morphological changes, and etc. Having said, having talked about this, let's say, short-term dynamics of the system, now I want to go a little bit into the historical trends. So salt intrusion in the delta is basically the key to land use, and as I already mentioned, there are various reports of increased salt intrusion in the delta. An interesting anecdote, first this, and we know that salt intrusion is basically the competition between ocean forces and river forces in a certain geometry and bathymetry. And in fact, any of these three that changes, salinity in the system would start changing. So that's where we have to look into where we want to look and find what is changing in the system. An interesting anecdote, in 2019, there was this BBC documentary that mentioned climate change in Vietnam destroying family life. And was this, I bring this here and then I come back to this. Going to the salinity in the delta and the historical changes. So if we look at, for instance, one of these stations in the Mekong Delta, if you look at just the red line and it shows the five highest percentiles of salinity in the delta, we do see an increasing trend line, and that also holds for P90, P50, so the median of salinity and all that. So we do actually, salinity is increasing in the delta, and any other thing. But when we started looking into different drivers of that, as I mentioned, river forces, so freshwater inflow. If we look at cumulative discharge and also minimum, the brown line is minimum discharge. In time, since 1986, it's actually been increasing. So that clearly doesn't explain this increase in salt intrusion. We talk about sea level rise and ocean forces. Let's look at that. We do in this station, we look at water level, which basically at estuary mouth. We do have that 2-3 millimeter per year increase. Even in this signal, you could partially see it. And if we look at tides, for instance, we also see a slight increasing in tides. So this red line is the seasonal, the dry season tidal amplitude, and we see that it follows a certain trend. And so this was a question mark. And then once we looked into within the delta, so 80 kilometers from the sea, and at these stations, for instance, in Meituan, and looked at the water level signal, and then we looked at the tides, then we suddenly see a significantly different trend. So this trend line that I just added is basically more or less parallel to the signal that we measure in the sea. But suddenly around this time, around 2005 and 6, we do see a breaking from that pattern. We do see suddenly a significant increased tidal amplitude. That for us was a key factor to dive into and see what is happening in the system at that stage. Going back to this documentary, referring to climate change as the main driver of change in the delta, there was an interview with a family that mentioned about 7 or 8 years ago, the weather changed drastically. And that was a public perception. But that 7 or 8 years ago, so interestingly, exactly coincided with this inflection point when we did start seeing significant deviation from the trends of increasing tidal amplitude. And for me, this was the first, the main signal that this is whatever that is explaining this. It explains salt intrusion, higher water level, and the city flooding that is continuously happening in the Mekong Delta, and bank erosion. Then we, of course, we dove a little bit deeper into the measured signals. We looked at, for instance, tidal propagation speed between different measurement stations. So between these two stations, how long does the tide take to travel in between the stations? And if we look at the historical trends, so this is basically, if we look at this one, here we have the year, so from 2000, 2005, 2010, and this is the number of minutes that takes the tide to travel from this station to this station. This has always been around 200 minutes, but then around 2005 and 6 starts dramatically going down. This is the same in many of these other estuarine channels, and here we see smaller changes, but then when we go upstream of Kanto, we do see more of the same pattern. Here it's not very obvious, but we do have this reduction in tidal propagation. Show here, and I didn't want to change the scale. So in this figure, you see that, but the only thing that actually can explain this is that tidal propagation speed is proportional to square root of g times gravitational acceleration times depth, and that basically translates to these changes in tidal propagation speed translate to 2-3 meters of deeper channels, and that was recently also validated by field measurements of Vasilopoulos and from Hull and Southampton University. Um, we can show a few of, for instance, bed level changes in some of these channels, as you see, for instance, between 2014 and 17, the same cross sections at places have changed nearly 5 to 10 meters, and this is an extreme variation over a very short period of time. And what do we learn from the, what can we say just from these observations? What we can say is, if we look at, for instance, this channel, this part of the system, I just flip it here. If this used to be the river bed levels, these river bed levels have lowered all the way to the ocean. If you look at this other system, the How River system, I just flip it here. This used to be the bed level. The bed levels have incised all the way to Kanto, and downstream of that, maybe less changes. Just from hydrodynamics, we could portray this picture, and this was validated by two sets of measurements, Allison and Allison and Vasilopoulos. So what drives this change? If we look at the sediment budget of the delta, the pristine river used to provide 160 million ton per year. And if we, well, more recent estimates are somewhere between 20 to 80 million ton per year, which is basically driven by significant reduction of 36 to 95% in sediment trapping, but all these hydropower development. And sand mining on its own adds 30 to 50 million ton per year, which here we have the distribution of that in the delta based on the existing licenses. And so this is basically the legal sand mining, and we cannot say much if there are also illegal events happening, illegal sand mining in the delta as well or not. But this is just this just says basically that sediment budget of the delta is if not just below zero, probably way below zero. So that's why we refer to this as yes, we talk about climate change, but we actually have to look at this system as an environmental change, which is driven by multiple drivers. If we look at just the problem of increased salt intrusion, sea level rise contributes to that, 3 millimeter per year, more or less. But relative sea level rise is actually much larger, average to up to 10 millimeter per year. Sediment trapping by upstream dams and excessive sand mining downstream both contribute to riverbed erosion and riverbank erosion, which results in increased tidal range within the Mekong Delta with the rates of 20 millimeter per year. And that also contributes to salt intrusion. And that basically this driver relative to this driver, the whole relative sea level is only covering can only explain 5 to 10% of the increased salinity and the observed trends, and the rest of that is basically driven by within the basin and delta dynamics, anthropogenic dynamics. So in fact, if we look at, for instance, the historical event of the 2016, this is model results, but it's very much close to, for instance, the observed salinity. This is more or less the median of salinity over the dry season. If the riverbed levels did not change between 2008 and 2016, this would be the extent of salt intrusion, which is much lower. You see the huge areas in between the two. And I'm not talking about the maximum salt intrusion. This is median. Let me go back. So if we look at the Mekong deltaic system, we mentioned that if this is a cross section of the delta, and we see that the river versus sea competition determines the salinity charts. salinity is influenced by natural processes such as tides, sea level rise, wind, waves, ocean surge, and fluvial discharge, evaporation, precipitation, and these are also influenced by climate change, but also by anthropogenic processes such as water demand or fluvial sediment starvation because of upstream hydropowers, and also the fluvial discharge anomalies, as well as sand mining in the delta that together with this sediment starvation leads to riverbed erosion and leads to saltwater intrusion. And you also have land subsidence, groundwater extraction, and land subsidence. We also have natural subsidence, but here we talk about the anthropogenic process. And also groundwater extraction that results in salt intrusion in the groundwater system. And if we look at the aggregate image, if we have a 3 millimeter more or less sea level rise, so not relative, but just the sea level rise itself, we have 20 millimeter per year increase in tidal amplitudes because of the anthropogenic processes. We have subsidence in the rates of 10 to 40 millimeter per year. We have surface water, saline water intrusion between 0.2 and 0.5 PSU or PPT per year. Riverbed erosions of 10 to 15 centimeter per year. Extreme sediment starvation, up to 80-90% of the sediment, fluvial sediment supply is basically non-existent. And fluvial discharge anomalies, which is normally actually increasing in favor of reducing salt intrusion. So having understood this and the deltaic system ins and outs as good as we could, we used a numerical model that we have developed. We, of course, integrated coastal and inland processes, upstream and downstream. Climate change and anthropogenic. Climate change was mainly projected in upstream discharge anomalies and downstream sea level rise, and anthropogenic processes were mainly projected in land subsidence and erosion. And of course, surface water and groundwater dynamics were sort of integrated in this modeling framework. We used the hydrogeological model of my colleague Philip Minderhout that was used for land subsidence projections. Basically he looked into different scenarios of groundwater extraction and projected delta elevation onto 2100. So we used this data. And of course, we used our 3D surface water model of the delta. So if you look at this, is basically these are the 7 estuarine channels of the Mekong Delta, and this is the estuarine salinity structure that is changing with tide. So these are 1 hourly intervals. Here is the tidal change, and we see that salinity is changing significantly with the tide up and down. It's just a demonstration of model, how the model works. Global 5 global climate models and 1 regional climate model, and we basically realized that the fluvial discharge in the Mekong Delta more or less increases by all of these models, increases towards 2060 with more or less the same trend, nearly identical trends, but beyond 2050 and 2060, then we start that these models start diverging. So we basically have an increasing discharge, fluvial discharge, more or less similar under both climate scenarios of AR5. We took 2 extreme So this is groundwater extraction rates measured since 1990, sorry. And then we chose one extreme scenario that basically groundwater extraction increases business as usual by 4%, as it has been following the last 25, 30 years. And a favorable scenario that basically groundwater extraction reduces 50% and stays at that rate after 2030. And then for river bed level changes and basically sediment loss in the system, we took two scenarios. One was extreme, which was basically losing 3 billion cubic meters of sediment until 2040, which is basically more or less the estimate what happened over the last 20 years, 25 years. And then a more favorable scenario that we are losing 1 billion cubic meter until the year 2040, which is 1/3 of the observed in the last 20 years. I mean, either in both scenarios, we assume that river bed level changes to stop after 2040 for multiple reasons. Basically running out of erodible material, or policy development that does not allow sand mining, or some sort of measures that bring sediment to the delta. Or so we assume that 2040 onwards there is no erosion. That's an assumption that of course can be challenged or not, but then we looked at all of these individual and combined effect of all of these drivers, and to see how salinity changes. So basically, if we look at only climate change, which is changes in upstream discharge and sea level rise, it's hard to see in this, but if you look at these percentages, which is showing the increase in salinity affected area, we're more or less talking about 6 to 7% until 2050. If we add land subsidence under moderate, so G, H, and I, under moderate scenarios, we add 1 or 2% extra salt intrusion in the affected areas. And under extreme scenarios, by 2050, we can add another, let's say, 4 or 5%. We may add another 4 or 5% of salinity affected area as a result of land subsidence. But even the moderate scenarios of river bed level changes suddenly significantly increases salt intrusion in the delta. So we see that under moderate scenarios of river bed level changes, we already go from 6% to 18% increase in salinity affected areas, and that under extreme scenarios. So if basically what happened in the last 20 years happens in the next 20 years, we're talking about 36 and maybe even more, 36% and 30% extra, or on top of climate change, and even maybe more depending on other factors. So this would potentially be the this would potentially be the image of the delta in the next 2-3 decades. Is absolute salinity, and this is the 50th percentile that I'm showing here. So it's not maximum salinity, but it's 50th percentile, which is basically a median, more or less what we can expect on an average condition. In these projections, we deliberately chose a very moderate year as our base, which was 2015. Which there was not too much of salt intrusion. It was actually a decent year, so we didn't want to portray like a very dark image. We tried to pick a good, let's say, more or less a decent average year baseline, and then see what happens to that year in the next 20-30 years. So if you look at the increase in saline water intrusion affected areas under pure climate change, RCP 4.5 and 8.5, we have this increasing trend. If we add moderate and extreme scenarios of land subsidence, pushes it up another, let's say, 40,000-50,000 hectare. But under moderate and extreme scenarios of river bed level changes, we suddenly have huge jump in the salinity affected areas. 2050 due to accelerated ice sheet melting, then you're talking about suddenly much larger trends of impact from sea level rise on top of all these anthropogenic drivers. So that brings me to my basically the concluding remarks that yes, we believe that in the short term, let's say in the policy perspective, 2-3 decades, anthropogenic processes determine the fate of the delta. And beyond 2050 and perhaps 2060, climate change and sea level rise will become much more of a dominant processes. So this talks about, of course, challenges and opportunities. The challenge is that a lot of these anthropogenic changes are difficult to reverse, not to say irreversible, very difficult to reverse. And the opportunity is that a lot of these systems are, a lot of these challenges are actually man-made and can be controlled by humans. So that's where we can perhaps try to influence the system development. And I should say thank you very much at this stage then.
Okay, yeah, thank you very much, for this fantastic talk. And that's we really learn a lot what the saltwater intrusion and all the dynamics, water cost, and the history, present, and the future. That's great. So let me now the audience, you are able to unmute yourself. If you have any question, please go ahead and ask Sepehr. Okay. Okay. Okay, Nicholas.
Hello. Yes, I'm Nicholas from Seawater Solutions, Vietnam. Thanks for your presentation. The first question I'd just like to ask is, given the changes in the hydrology of the delta that you're proposing, worst case scenario, what kind of livelihood opportunities do you think people living in the area would have? How much would their lives change, and would they be able to continue living in these regions or not?
There are multiple drivers of change. So we talk about land subsidence, we talk about salt intrusion. The opportunities that are there, for instance, the seasonality of the Mekong Delta means that basically during the wet season, you have other challenges such as, for instance, flooding, but you don't have problem with salt intrusion. And then the river provides you with huge amounts of water that can potentially be stored and used during the dry season. So any system that tries to use that variation can basically help the solution to freshwater supply lies in that equation, in my opinion, how we can find this balance. When it comes to the land use, of course, as I mentioned, salt intrusion is one of the key factors in determining land use. Yes, if salt intrusion increases up to, let's say, right now we have values of, let's say, 40-50 kilometers. If it reaches on an average year, let's say 100 kilometers, that means that huge amounts of areas that are now doing rice, they basically have to change to aquaculture or perhaps mixed systems, like in the wet season do something and in the dry season do something else. So this study might have a very dark image of the delta, but like I said, it's all about adaptation and looking into these environmental pathways and try to see how we can adapt to these changing conditions, how to reduce the impact of processes, and how we can promote positive, let's say, trends. For instance, how can we increase, let's say, sedimentation in the delta, although the system does not have too much sediment, but still it does have a huge amount of organic and inorganic suspended sediment that can be used to, for instance, gain elevation, or if you look at let's say the groundwater system, can we use the groundwater system to store water in the wet season and then use it in the dry season? So all these changes, of course, they have to be accompanied by enforced regulations, such as, for instance, sand mining is poison, and not only within the delta, but also beyond the delta. Same holds for groundwater extraction and uses of groundwater resources. So all these challenges, I'm not that pessimistic because I also believe that Vietnam as a country is a country that actually, when they decide to make a change, they can do that relatively, let's say, forcefully and strongly. So I am not that pessimistic, but to make the right changes, and I say the right changes, then you have to have this overall image in mind and not resort to, let's say, isolated solutions that only look at, for instance, river bank erosion, or only look at a certain aspect of the delta. So this is basically my understanding of.
Good. Okay, Sepehr, we have a question from Laurent, Netherlands Embassy in Hanoi. Okay, Laurent.
Yes, Sepehr, thank you for
Laurent.
your presentation. Very interesting. You know, for a while I have been puzzling about the Vietnamese strategy to block the canals at the end of the rain season in order to store fresh water for the farmers. And I was wondering whether that measure was actually worsening the salinity intrusion. It might be a very local solution to prevent salinity intrusion in the canals, but it might push up the salinity in the main rivers into areas that have never experienced salinity. Now, this is somehow, can you relate, let's say, these trends to your research findings, or did you relate also your conclusion that it must be the riverbed that is deepening rather than the channels that are being blocked as an explanatory factor in your research?
Yeah, now it's a good question. I haven't looked exactly into this, but there are two. We did two exercises. We looked at the total volume of all these primary and secondary canals relative to the overall water that comes in and out of the system, so the tidal prism, and we come to a very small value. So I don't. And that small value, let's say, top of my head, a few percent. I can't remember the exact number, but that few percent, in my opinion, cannot influence if some of those channels are closed for salinity in the dry season. I don't think that has an influence on salinity going further upstream. It's mainly the riverbeds of these rivers that are 3 kilometers wide and 20 meters deep, and these huge amounts of the salt flux that goes upstream. We also looked at in our projections, we looked into, as a sensitivity analysis, we said, okay, we're going to remove all these sluice gates and dams and see how the delta looks like if it's all natural. And well, I don't have it in this study, but that's basically a huge amount of volume that actually half of the delta will be saline. So these sluice gates do have an impact. Whether it's we can talk about their functionality, how effective it is, and do we have to invest in that or not? That's a totally different topic. But as it is, I don't think they harm salt intrusion length.
Well, you should see, Sepehr, you should see you need more money to study this. Laurent, is that okay, his answer?
Yes, I like the answer very much. But I was wondering, in your research, you showed that the deepening of the riverbed was particularly a little bit more upstream and not at the estuaries. So you kind of you will get a kind of a hill, let's say, in the riverbed when it comes closer to the ocean. That hill, so to say, doesn't it prevent further salinity intrusion, or the salinity just goes over it in a wave and then enters into the deeper section?
Yeah, so that increase in that so-called hill is basically a natural system in all estuaries. So salinity, the estuary depth sort of starts increasing mouth, and then it goes to the sea and the shelf and goes down again, and then you go upstream, the channels start getting deeper. So that's a natural thing that's part of the system, and salinity, as we talk about it, is given that natural pristine condition. But once the system is changing, it's true that I said some of these changes are not happening downstream, but I distinguish the two systems. If I look at this Tien River system, and I see that these changes are happening all the way to the estuary mouth. So even lower estuaries are deepening, and I showed that in the tidal propagation analysis. And if we go to this Hao River, we expect that downstream of Kanto, so the last 70-80 kilometers, there's not too much change happening in the riverbed levels, or at least in the total riverbed levels. But
Sepehr, actually, based on the estuary dynamic, if we have that trough in a little bit middle or upper reach, that will definitely increase the saltwater intrusion, because when the tidal water flow in, remember, fresh water stay on the top, salt water at the bottom. If there is a low trough there, the saline water will stay longer in the estuary. Exactly. I mean, that's I think Laurent's question can answer about that.
Yeah, no, that's right. So it's that deepening, it just worsened the situation, and this increase in river beds, or basically this shallowing of the estuarian beds towards the estuary mouth, it's part of the natural system, and then in deepening worsens the entire salt intrusion process. So I hope that explains.
Okay, so. Nice. I have a question related to this. You mentioned around 2005, 06, the salinity situation become worse, right? Salinity intrusion.
Yeah.
One slide you mentioned about that, right? Somewhere.
Here I have the long-term trends of salinity.
Yeah,
we can look into this.
That's very interesting, because let me show one thing. And are you able to see this one?
Not yet, but now I can see.
Based on the whole Delta survey, the whole the shoreline, the whole thing together can have a negative value starting around 2005. And if you look at the area, the delta area change is also 2005 or 15. That time, it's like a starting point to, I call it, from a constructive turn to a destructive.
Correct. Yes.
Based on your presentation, the sediment, reduced sediment, increased sediment mining, and even subsidence, all things make the whole Mekong Delta. There's no way for the Delta have a negative gain. Actually, some area you see have 20 meters every year, 20 meters shoreline retreat. If we keep having the shoreline retreat, not only near the channel, but actually particularly around the Camol, East Camol, this area, the saltwater intrusion will become worse and worse, severe and severe.
Correct. Actually, so in my presentation, I showed that so subsidence as it is does not necessarily increase salt intrusion too much, especially in the estuarian systems. But if you go far from the rivers, go to Pakliof and Kamau Peninsula, there any elevation loss, sea level rise and subsidence then also significantly contribute to salt intrusion. So they do increase, but those are areas that are already saline. So perhaps less of a concern. I wouldn't say no concern, but less of a concern. And what I've been calculating is areas that will become saline in time. But this is very interesting. I do know this paper, but I did not see this 2005 threshold. It's interesting.
You need to read it carefully and reference.
I have to read a bit more carefully.
But anyway, I'm very glad maybe we can both put the data together, because I have a lot of nearshore, offshore data. Then you have the onshore in the river channel data. If we put them together, this gives us the full picture.
Exactly. Extremely interesting.
Okay, let's back to the audience. I know Sale, I don't know the name. The Sale, you can you unmute yourself, introduce yourself?
I'm Zoe. Hey, Sepehr. I was watching on YouTube, but I came on Zoom because I have some questions. So mine are bigger picture. Two of them. The first one is you, in the conclusions from your study, you noted that after 2050, climate change will become the main driver. Is that correct?
I would say it will become a...
Oh, you're frozen.
Apology. Because until 2050, anthropogenic drivers are definitely dominant, and climate change is a smaller factor.
Okay, well, by that logic, then, what is our best chance of mitigating this? Should we intervene before that point at which, climate change becomes the main issue, or because surely there's a point at which it kind of becomes out of our control, right?
So that point is the point you want to avoid. What you want to do is basically try to prepare for that and look at, so you have to monitor these changes, what's called adaptive pathway planning. So you have to monitor these changes. First, you have to act on your negative drivers. So say sand mining, hydropower developments. These are not challenges that are limited to the Mekong Delta. It's related to the bigger Mekong Basin. So it also needs active diplomacy to the upstream countries and all that. So you basically have to minimize the negative drivers of change, the system stressors, the ones that we can influence: sand mining, groundwater extraction, hydropower development, and all that. By that, we have uncertainties in climate change. So we have to monitor the system, and we have to already start adapting to that change. If you ask me, we have to prepare for all of these scenarios that I projected by the year 2050, and then every 5 years reevaluate our adaptation strategy, because the system is extremely dynamic. These projections have a lot of uncertainties, but also climate change on its own has a lot of uncertainties. And I just showed that if, for instance, sea level rise accelerates by 2030, 40, and then we have let's say 60 centimeters sea level rise in 30 years from now, then we are talking about also the impact of sea level rise is much larger than what we think it is at this stage. So yes, basically, I don't want to portray a doomsday scenario, but today is already late. That's the point. Yesterday we should start yesterday or a few years ago this adaptation.
Okay, so we have next question. We have from Vietnam. Han Phuc, are you ready?
Sorry, one more question.
Oh, okay, quickly.
Yeah, quickly. This is a quick one, actually. It is a little ignorant. Is this the first time that these kinds of projections have been made in terms of, that point at which 2050 at which the dynamic changes?
Yes, it's there has been projections by 2050 before, but they excluded anthropogenic drivers and many other drivers, and we just have the paper accepted for publication, Nature Communications, Earth and Environment. In the next couple of weeks, it will be out. With these projections and the background of that. And there we also explain a couple of other studies that looked into projections, what was lacking in those studies. And yeah, so that's why, for instance, the 2015 projections of 2050 was exceeded in 2016 within 1 year. So that's
okay.
There's your hook. All right, thank you very much.
Yeah, okay.
So I think we have a question from Vietnam. I mean, that's actually exactly what we want. We want our talk series can help the people over the Delta, Okay, Han Phuc, Professor Han Phuc, please go ahead from Ho Chi Minh City.
Okay, I'm sorry, I know that it's a little bit late, but I just to have some small questions about. First, thank you very much for your interesting presentation. From that, we have the general view of the what about the intrusion in our Mekong Delta. But in my opinion, have you ever to make the comparison what in about the sun intrusion also in Mekong Delta, but we can divide it into parts. One, the Mekong Delta is belonging to the Mekong rivers, and another part. In the south, it went down, for example, in Park Lieu or Kamau, it's not to the main impact by the Mekong River. Do you understand what I mean? So that the sun intrusion mechanism in two parts, maybe some differences.
Yes.
Some difference.
Correct.
Yeah,
that's
and for because here you also to make about the sea level rise and the subsidence. But I think the subsidence in the upper layer, upper Mekong rivers and the upper Mekong Delta and the lower Mekong Delta, maybe some difference. Have you ever make the difference or made a comparison of these?
Yes. So our let me share one screen again. 1 second. Very good question. So let me see. You see my screen?
Yeah.
Yes.
Not yet.
Yeah. So when we looked, this is showing salinity increase, spatial variation of salinity increase across the delta. So for instance, if I zoom on this side, this dark purple is showing something in the order of, let's say, 10 PSU increase by the year 2050.
Yeah.
If I go further, so for instance, if I just stick to climate change and how, for instance, river discharge increases and sea level is rising, what we see is that actually in the estuarian channels, salinity is not increasing due to climate change. But if we go distant from the river, where we talk about, for instance, Kamau, Bac Lieu, and those provinces, then the sea level rise is actually the main driver at times in already a threat for those provinces. So that disintegration of the river system and the rest of the distant part of the delta is actually already there in this modeling exercise. Same holds for land subsidence. So for land subsidence, we did not use average values. We actually looked the exact spatial variation of subsidence. So in some places, like further upstream and downstream, subsidence was different. We had different rates of subsidence, and that's what translates into this image. So yeah, we did look into those factors, if I have understood correctly your question.
Yeah, but because when we thinking about the dynamics, I think that the dynamics sometimes it's also different as well. Because here is the main impact of the rivers. Yeah, but the lower we have a difference because we have many channel and breaks. Yeah. So that's some dynamics, the dynamics. I would like to know about the dynamics in the higher and the lower. Yeah, sometimes it's different, the impacts.
That's true. I do understand there can be significant complications there, but I still think that the way we have set up this modeling framework, it captures most of these dynamics as it relates to the river and the channels, because we have the full system of primary and secondary channels. We have incorporated all the dams and the sea surrounding the delta, so those dynamics should be there. Although of course there are other man-made dynamics that may be missing in our system. But and same holds for land subsidence, that we try to look at these variations in time, and of course the system. And that's actually this question that you're raising is one of the reasons that I thought when we were doing this exercise that we actually need a larger scale model that extends all the way upstream and all the way to the ocean. We cannot cut the model at the estuary mouth, the 3D dynamics, all these processes. That's why we thought, okay, let's just make it complicated, as complicated as it gets. And then let's let the supercomputers run and do the job. It was difficult, I mean, but let them do the job. And
But maybe we will change another project, the big project. First. Is it okay, Paul?
Sure, we should do together.
Let's do 2050 to 2100.
Hanfak and Sepehr, maybe we can think about organize a Mekong Delta specifically workshop. We talk about the Mekong, maybe 2 or 3 days online. That will be, I think, pull all the expertise together. I think it will be very interesting.
I think so too. I think so.
Yeah. Okay. The last question, Nicholas. Nicholas, you have one more question?
Yeah. Hello. Quick one. What are the best adaptation methods, in your opinion?
It freezed.
Different. That's more than a $1 million question. But so there are mitigation measures and adaptation measures. I mean, right now we are thinking about any adaptation strategy that promotes flooding and sedimentation in the delta, that basically restores the natural system, in my opinion, has an advantage over any other solution. So that basically means if you have to open the floodplains to seasonal flooding, that brings nutrients, that brings a sediment to the delta. It partially compensates for the land subsidence, and that's one part of the problem. There are measures that have to be taken. It's inevitable that aquaculture becomes much more of a norm in large parts of the Delta, in my opinion, in the next decades. No matter how vigilant we are at this stage about adaptation and reducing the impact of anthropogenic processes, we have to make sure that we are ready for a certain level of increase in salinity, which means that adaptation to saline water and switch to aquaculture, sustainable aquaculture, is one of the solutions. Right now, for instance, WWF is actually promoting a strategy of a mixed rice and shrimp system. This this rice and shrimp system it's sustainable, so it's not using groundwater, and it tries to maximize water intake and sedimentation in the rice and shrimp farms, basically to do elevation gain. And that's a fabulous example of a potentially big solution adaptation measure for large parts of the Delta. So this switching from fully rice to mixed system of rice and shrimp, sustainable. And then this goes hand in hand with reducing the negative factors, as I mentioned, sand mining and groundwater extraction. And I honestly, I think the devil is in the transboundary water management. There's a huge impact from whatever that happens in the bigger Mekong basin on what is happening and what we see in the Delta. For instance, this hydropower development, actually there are some new positive developments. For instance, Cambodia banned hydropower development while they had plans, and they did that in 2019. They banned hydropower development, and in my opinion, that was one of the major decisions. It was a historical moment, in my opinion, that they realize that this is so toxic for the system. So yeah, so for instance, the role of Tonle Sap the retention area that used to provide the Delta with fresh water in the dry season, for the big part of the dry season. But the Tonle Sap Lake, because of the hydropower operations that basically taper the flood pulse, it's never filled. And therefore, already in December, January, the Tonle Sap Lake is empty. I have difficulties to imagine how, but one of, for instance, major, I mean, we talk about retention areas in the Delta, right? That's one of the adaptation strategies, let's say, to develop retention areas in the Delta, store fresh water in the wet season, use it in the dry season. But we have the biggest retention area in the world in Tonle Sap Lake. So I think, for instance, if we look at how we can manage not only the river discharge, but also the river water level, so that the Tonle Sap Lake is sort of restored as a retention center. That for me, it's one of the go-tos. It has to be explored. It hasn't been studied whether it's actually even possible with all those dam developments.
Okay.
Yeah. So that's these are the number of things that I just hit my mind at this stage.
Okay, nice.
I guess we're running out of time.
Yeah, okay. Thank you, Sepehr. And I think, it's 1 hour and 20 minutes. And thank you for those who still stay online. And this is a great talk. I already put on the link of this talk and any other talk. So on the chat, so you are welcome to forward the link to your colleague, your student. And so again, Sepehr, thank you very much. And
thanks a lot for organizing, Paul.
I see you next week for more talks. Okay, thank you very much. Okay,
bye.
Bye-bye.
Have a good day, evening, afternoon.
Yeah, sure.
Bye.
Thank you. Bye.
Bye-bye.